In this video, I will give a brief overview of quantum statistics. So in statistical mechanics, one usually considers particles classically. That is, we use Newton's laws of motion to describe them. We then consider a system of many of these particles. We use statistics to derive the macroscopic properties of this system. That is the essence of statistical mechanics. Okay, so what if we instead begin by considering a quantum particle? That is a particle described by quantum mechanics. So it has a wave function which evolves according to Schrodinger's equation. Now let's say we have a system of many of these particles, just like in the previous case. Okay, so the question is, what if we do statistics on this system? What would be different? This problem gives birth to quantum statistics. And this will be the main focus of this video. So I want you to think for a second. What will be the difference? What do we have to change from the previous statistical treatment? Clearly, it must be something related to the description of a single particle using Schrodinger's equation. But what is it specifically? Well, it turns out that in the classical approach, we can fully describe a particle's trajectory. So if we solve Newton's laws of motion, we can know the particle trajectory throughout time, and therefore we can label each particle in the gas, throughout time we follow their trajectory, and thus we have a history of each particle's motion. We know, we can track them. So in some sense, we can say that these particles are distinguishable. Okay, so what happens in the quantum scenario? Well, in this case, Schrodinger's equation does not give us a specific path or trajectory. There is not a well-defined trajectory associated to the particle. Rather, the Schrodinger's equation gives us the evolution of the wave function of the particle, and from there we can get a probability distribution of its position, for instance. So, okay, if we cannot have a specific trajectory or history associated to each particle, we cannot distinguish them. And that is a really big difference. And I would like to point out this is not a problem of our instruments. Because in the classical scenario, we can, if we use a sufficiently powerful instrument, we can track each particle. It would be really difficult if we have a system of 10 to the 23, but it is indeed possible. At least that's what theory says. In the quantum scenario, even theoretically, this is impossible. So it is a fundamental and intrinsic aspect of the quantum theory of many particles. They cannot be distinguished. And that changes statistics significantly. So, to illustrate this, let's consider two persons. Alice and Bob, that are going to the cinema. They have two available seats, and they have two choices. So Bob can sit here, Alice can sit here, and the other possibility is that Alice can sit here, Bob can sit here. So these are two different states of the system. If we were studying this with statistical mechanics in the partition function, this would lead to two different addition terms, because these are two microstates associated to the system. In the quantum mechanical states, instead of having Alice and Bob, we are saying these two are identical clones. So it doesn't matter their choice of seat. The end result will be the same. We will not be able to distinguish them. So this corresponds to a single microstate. And therefore, in the partition function, this would be a single addition term instead of two. So that is the distinguishing feature indistinguishability. Is the distinguishing feature of quantum statistics. So now I would like to be more precise about what does indistinguishability mean mathematically. Let's consider a system of a gas of m particles. And Qi, we use Qi to denote the coordinates that fully describe the ith particle. Ith particle. So at a certain state, the gas would be described by a wave function, which is a function of the coordinates of each particle. Okay, so what does indistinguishability mean in this context? If we consider the ith particle and the jth particle in the gas, and we exchange their position in the wave function, if we exchange the roles, so to speak, the physical results should be the same, because particles are indistinguishable. Okay, so the physical results in quantum mechanics are associated to the norm of the wave function. So this means that the norm after changing the ith and the jth particle should be the same. Okay, and one can show that this implies either two consequences. Firstly, the first option is that the wave function remains unchanged. So we interchange here, and the wave function is the same. So that is one possibility. And the particles that satisfy this condition are called bosons. The other possibility is that Okay, so we exchange particles and minus sign appears. So in the first case, we say that the wave function is symmetrical, and in the second case, we say that it is antisymmetrical. And the particles that satisfy this are called fermions. And in both cases, exchanging the position of the ith and jth particle does not modify the physics of the system. Okay, so now that we have a more precise idea of what indistinguishability means, let us consider a very specific but important scenario. Let's say we have two particles in the same quantum state. Okay? Okay, so let's consider the wave function of the whole system. And we are saying that in that system there are two particles that live exactly in the same quantum state. Okay, so if we have the wave function of that system, we know that exchanging the ith and jth position of these identical particles in the same state must not change the wave function, regardless of if this is a boson or a fermion. This must be true because these particles are in the same state. Okay, so now let's say additionally that these particles are fermions because of the antisymmetry that I mentioned previously. So for fermions, this means that exchanging the ith and jth particle in the wave function introduces a sign in the wave function, a minus sign. So this implies that the wave function must be itself times a sign. So that implies that the wave function is zero, or in other words, that state is not possible. What we have concluded then is that for fermions, a state where two particles exist in the same quantum state is not possible. With this knowledge, let us then consider a simple example of a gas of two particles which can live in two different energy levels. Level 1 with energy epsilon 1 and level 2 with energy epsilon 2. So we will do statistics on this system in three different scenarios. Firstly, the classical scenario, then the quantum scenario, and this quantum scenario has two other possibilities. Either the particles are fermions or bosons. So first, the classical scenario. Let's say these particles are A and B because they are distinguishable. So we want to compute the partition function of this system, because from the partition function we can get all the thermodynamics of the system. So that is our objective. And remember, oh sorry, this is a sum actually. So the partition function is a sum over all microstates of the system. Okay, so we need to find what are the possible microstates. First, A and B can live in the same energy level, that is one microstate. Then A and B can be in two different energy levels. Now, B can be in energy level number 2 and A in energy level number 1, and that is a different microstate. And finally, the two particles can be in the first energy level. Okay, so considering these energies, this leads to the following partition function. E to the minus 2 beta epsilon 1 plus 2 e to the minus beta 1 plus okay, and these two comes from these two microstates, right? Okay, that is the classical scenario. Now, the quantum scenario with bosons. So first, the most important thing about the quantum scenario is this indistinguishability of the particle. So A must be equal to B. And so we have the following microstates. Either the two particles are in the same energy level, either they are in two different energy levels, or they are in the first energy level. There is one microstate less than in the classical scenario because the particles, again, are indistinguishable. So these two reduce to just one. And from here we can see already a big difference in this very simple system. So the partition function in this case would simply be the same except that we do not have a 2 here, because we only have one microstate where two particles are in different energy levels. So finally, the quantum scenario for fermions. And as I mentioned earlier, fermions cannot be in the same quantum state. So this is no longer possible. This is no longer possible. And the only remaining possibility is this. And so the partition function is simply minus beta plus 2. Okay. So we can already see that the quantum statistics differ significantly because of the indistinguishability of the particles, and there are two different possibilities within this quantum regime. So I hope this video was useful, and bye.